Welcome to today's paper reading. Today's paper is titled, Towards Scalable Automated Alignment of LLMs, a Survey. This paper was published on the AR14 preprint by Boxi Chao and colleagues from the Chinese Information Processing Laboratory, Institute of Software, Chinese Academy of Sciences, Alibaba Group, and University of Chinese Academy of Sciences. The alignment of large language models, LLMs, is crucial for meeting human needs. As LLMs surpass human capabilities, traditional alignment methods based on human annotation are becoming insufficient. There is a pressing need to explore new automated alignment signals and techniques. This paper reviews emerging automated alignment methods, categorizing them into four major types based on alignment signal sources. It discusses the current status and potential development of each category, exploring the underlying mechanisms that enable automated alignment. The paper also examines the essential factors that make automated alignment technologies feasible and effective, particularly in the context of LLM capabilities exceeding those of humans. Figure 1 presents illustrations of four representative paradigms for automated alignment in large language models, LLMs. These paradigms include aligning through inductive bias, behavior imitation, model feedback, and environment feedback. The figures are generated using DALL-E, a generative model by Ramesh et al., 2021. This visual representation highlights the different approaches to achieving scalable and effective alignment with minimal human intervention, which is crucial as LLMs continue to evolve and surpass human capabilities. The rapid advancements in large language models, LLMs, have significantly transformed the field of artificial intelligence. Alignment, which involves shaping LLMs to adhere to human intentions and values, is crucial. This often includes teaching LLMs to follow principles like being helpful, harmless, and honest. Traditionally, alignment has relied on manually annotated data, which is both expensive and challenging to scale. As LLMs' capabilities approach or even surpass human levels, the quality and relevance of human annotated data have become questionable. This has led to the emergence of automated alignment methods, which aim to construct scalable and high-quality alignment systems with minimal human intervention. These methods are essential to address the core challenges posed by the rapid development of LLMs, where human annotation is either infeasible or extremely costly. This survey explores various automated alignment methods and their potential future directions. The scope of automated alignment in AI systems is crucial for ensuring that machine behaviors align with human values and expectations. As AI systems, particularly large language models, LLMs, become more complex, aligning these models with nuanced human standards becomes increasingly challenging. This has led to the development of methodologies known as automated alignment. Current studies of automated alignment can be categorized into four main types: inductive bias, behavior imitation, model feedback, and environment feedback. Inductive bias enhances models with assumed generalizations or rules. Behavior imitation trains AI systems by mimicking aligned models. Model feedback integrates insights from other models. And environment feedback adapts the model based on real-time data. The evolution towards automated alignment suggests a future where AI systems can self-regulate and evolve alignment protocols autonomously, promising advancements in AI governance. However, human oversight remains essential to ensure ethical boundaries and societal norms are respected. Figure 2 provides a comprehensive review of scalable automated alignment methods, focusing on the source of alignment signals. It categorizes these methods into four main categories: aligning through inductive bias, behavior imitation, model feedback, and environment feedback. Each category represents a different approach to achieving alignment with minimal human intervention, highlighting the potential for scalable and high-quality alignment systems in the rapidly evolving field of artificial intelligence. Figure 3 illustrates the alignment of large language models, LLMs, through three representative inductive biases derived from the inherent features of LLMs. The first bias, H1, uses uncertainty as an indicator of helpfulness, where higher probabilities assigned by an LLM to a given answer correlate with correctness. The second bias, H2, demonstrates that LLMs can judge, critique, and refine their responses, enhancing safety and quality. The third bias, H3, shows that LLMs can effectively learn in context, using robust in-context learning abilities for automated alignment. These biases collectively guide the model towards behaviors and decisions that meet human standards and expectations. Aligning through inductive bias is a promising approach for automated alignment. This method leverages inherent assumptions or constraints to guide model learning and decision-making. One of its primary advantages is that it does not require additional supervisory signals, thus avoiding the high cost of obtaining additional annotated data. It also has the potential to address the scalable oversight problem, allowing models to continuously self-improve beyond human knowledge. The key inductive biases discussed include using uncertainty as an indicator of helpfulness, the ability of LLMs to judge, critique, and refine, and effective in-context learning. Additionally, inductive biases from the organization of LLMs, such as task decomposition and self-play methods like generator discriminator and debate, are explored. These methods aim to enhance model capabilities and address complex alignment challenges. Figure 4 presents a calibration plot comparing the probabilities associated with the model's output against the probability that the answer is correct. The x-axis represents the model's output probability, while the y-axis indicates the probability of the answer being correct. The plot highlights two key areas. In the low probability region, a gray area may reflect don't know responses substituting some low confidence answers. In the high probability region, the gray area signifies overconfidence. This comparison between pre-trained large language models, LLMs, and aligned LLMs demonstrates that alignment for helpfulness can lead to miscalibration, which is detrimental to iterative self-improvement. Figure 5 illustrates the alignment of large language models, LLMs, through three representative inductive biases that arise from the organization of LLMs. These biases include task decomposition, where complex problems are broken down into simpler subproblems, generator discriminator self-play, where a generator and a discriminator engage in an adversarial game to improve output quality, and debate-based self-play, where multiple adversarial generators and a discriminator engage in a debate to enhance truthfulness and reasoning. These methods aim to improve the alignment and performance of LLMs by leveraging different organizational structures and learning paradigms. Figure 6 showcases representative studies focused on aligning models through behavior imitation. This method involves collecting high-quality instructions and using a supervised model to generate alignment signals, which are then used to align the target model. The studies are categorized into strong to weak distillation and weak to strong alignment, highlighting various strategies and methodologies employed in these approaches. The chapter discusses the strategy of aligning through behavior imitation, which involves collecting high-quality instructions and using a supervised model to generate alignment signals. These signals, which include instruction response pairs and preference data, are then used to align the target model by imitating the produced behaviors. The process of instruction construction is detailed, highlighting methods such as in-context generation, instruction evolution, and instruction back-translation. Additionally, the chapter categorizes studies into strong to weak distillation and weak to strong alignment, with a focus on preference-guided distillation to align the student model with human preferences. Figure 7 illustrates the process of aligning large language models, LLMs, through feedback generated by reward models. These models automatically produce feedback in scalar, binary, or text formats, which helps in aligning LLMs with human values. This automated approach significantly reduces the need for human annotation, making the alignment process more efficient and scalable. In this section, we discuss how model feedback can be used to align large language models, LLMs, with human values. We categorize the feedback signals into three types: scalar, binary, and text signals. Scalar rewards are generated by a reward model that estimates human preferences, commonly used in reinforcement learning from human feedback, RLHF. Binary verifiers are used for objective tasks like mathematical problems, assessing the correctness of final answers and reasoning steps. Text critics provide semantic feedback, enhancing the alignment of LLM outputs with human values. Each type of feedback signal presents unique challenges and opportunities for automated alignment. Figure 8 illustrates the alignment of models through various types of environment feedback. This includes social interactions where models communicate to build multi-agent systems and gather alignment signals. Human shared values provide judgments from human societies to calibrate internal model values. Additionally, feedback from tool execution and embodied environments allows models to interact with external tools and physical spaces to receive instant feedback, enhancing their alignment with task goals. This section discusses how alignment goals can be automatically obtained from existing environments to achieve automated alignment of the target model. The focus is on four main areas: social interactions, where models communicate to build a multi-agent system and collect alignment signals; human shared values, where models receive judgments from human societies to calibrate their internal values; tool execution feedback, where models interact with external tools to receive instant feedback; and embodied environment, where models act as language interfaces in a physical world and get rewards based on task goals. For social interactions, recent advancements in large language models allow for the construction of LLM-based agent systems to simulate human interactions, enabling the gathering of alignment signals with more scalability. In human shared values, alignment signals are derived from collective human efforts, aiming to synthesize various human ideas into a set of target principles for model alignment. Tool execution feedback involves using tools to expand the capabilities of large language models and receive direct signals for validation and enhancement of outputs. The paper investigates three core research questions regarding automated alignment mechanisms. First, it examines the underlying mechanism of current alignment, focusing on behavioral norms transfer and knowledge learning. Feature-based analysis reveals that alignment primarily affects stylistic tokens rather than knowledge-intensive tokens. Second, the paper explores why self-feedback works, highlighting the role of models' knowledge that cannot be directly used for generation but can be employed for feedback. It also discusses the debates around the effectiveness and biases of self-feedback. Lastly, the paper investigates the feasibility of weak-to-strong alignment, showing that LLMs can generalize from core principles and limited supervision to achieve significant alignment effects. Simple methods can significantly improve weak-to-strong generalization, but the fundamental reasons behind these capabilities remain to be fully understood. The survey categorizes scalable automated alignment techniques into four primary domains: aligning with inductive bias, behavior imitation, model feedback, and environment feedback. Despite advancements, significant research gaps exist, particularly concerning the reliability of self-feedback and the feasibility of weak-to-strong generalization. Addressing these gaps is crucial for the safe application of large language models. Future research aims to bridge these gaps, potentially enabling LLMs to conduct their own alignment research, improving safety. The Super Alignment Project outlines an ambitious plan to develop an alignment research expert, shifting human cognitive burden from generation to evaluation. Recent advancements in LLMs show potential to address domain-specific expert-level problems, illustrating how AI systems could eventually surpass human capabilities in tackling alignment issues. Thank you for watching.